You can stand before a plain wall punctured by two narrow openings, dim a source until light arrives in whispers, and watch meaning appear. No thunderclap announces it, no chorus sings, just one dot on the screen, then another and another, until a pattern gathers itself from what once seemed like noise. The double-slit experiment is not a spectacle, it is a meditation. And meditations reveal character. This one reveals the character of nature when questions grow delicate. Tonight, we will keep company with that delicacy. We're going to walk a very long road at a human pace. We will start with the earliest arguments about whether light is a wave or a thing, Huygens' ripples, Newton's corpuscles, Young's audacious slits. We will feel the 19th century's confidence under Maxwell's equations, then the 20th century's honest doubt under Planck and Einstein. We will sit with Bohr's complementarity, which is not a riddle so much as a boundary line for sensible questions. And then we will trace, carefully, how modern variations, the quantum eraser and delayed choice experiments, do not overturn causality or invite magic, but ask us to speak more precisely about information and the structure of quantum states. Before we do this, let me set expectations and explain why you should trust the path we'll take. Expectations and credibility. Here is what you can expect from the next hour of your attention. First, clarity without betrayal. I will not hide behind equations, but I will not say anything an equation could not defend. Second, faithful experimental storytelling. We will name components, slits, polarizers, beam splitters, detectors, and describe what they do without romance. And third, a slow, steady separation of what the experiments show from what we, understandably, want them to show. And fourth, a gentle, emotionally grounded narrative that respects the wonder these setups deserve without selling you superstition. As for credibility, I have spent years translating physics for audiences who range from high school dreamers to working scientists outside the field. I have learned that precision and poetry aren't rivals, they are allies. When a metaphor helps, you will get it. When it misleads, I will retire it. And when a silence speaks better than a sentence, I will leave space. If this is the kind of journey you want more of, subscribe to the channel now, so each new chapter in our series on quantum reality finds you the moment it's ready.
Act 1. The first voices, corpuscles, waves, and a choice deferred. The 17th century gave us two master narratives for light. Isaac Newton, whose calculus tamed the planets, believed light was made of tiny particles, corpuscles, shooting straight, bouncing off surfaces, and bending in media by forces like gravity's gentler cousin. He could account for reflection and refraction with admirable economy. Across the channel, Christian Huygens held a different picture, light as expanding waves in a medium, an ether he imagined but we no longer need, bending gracefully around edges and interfering like ripples on a pond. For a while, authority carried the day. Newton's name made a kind of weather. But nature is a better authority than any person. In 1801, Thomas Young stood a simple device between debate and truth, a light source, a thin barrier with two slits, and a screen. If light were particles, you would expect two bright patches behind the slits, perhaps a bit fuzzy. Instead, Young saw a ladder of light and dark bands, interference fringes, the clear handwriting of waves. Where peaks met peaks, brightness. Where peaks met troughs, cancellation and darkness. This was not showmanship. It was an invitation to think more carefully. If two ripples can arrive at the same place and either reinforce or cancel, then the world allows superposition, multiple possibilities overlapping, their phases determining what you observe. The 19th century took the invitation and ran. Augustin Jean Fresnel and others tightened wave theory into a precision instrument, And then James Clerk Maxwell wrote equations that married electricity and magnetism and revealed that light is an electromagnetic wave traveling at a constant speed. The same speed, it turned out, that Einstein would later make the speed limit for the universe. For a moment, it seemed we were done. Light was a wave. Close the book, go home, enjoy the triumph. But, as often happens in physics, a corner case arrived to pry the book back open. Act 2. The Begin Again. Quanta, photons, and a world with two names. At the dawn of the 20th century, Max Planck tried to explain the spectrum of hot bodies, the way they glow from dull red to white to blue as they heat. The math yielded a miracle only if energy came in discrete packets. An odd trick, he thought, useful, perhaps temporary. Einstein went further. The photoelectric effect, electrons leaping from metal when light shines, made sense if light itself sometimes behaved as if it came in quanta, localized hits we now call photons. Now the plot sharpened. Double-slit interference demanded waves. The photoelectric effect demanded particles. And as experiment followed experiment, the world refused to be one thing. It seemed ready to be whatever careful questions asked it to be. Quantum mechanics, the framework built to house that duplicity, is both austere and generous. Austere in its rules, generous in the variety of phenomena it allows.
Act 3. The double-slit, one particle at a time. Let's bring the double-slit into the modern lab. Imagine a source so dim it emits one photon at a time. Each photon travels to the barrier and must, you think, choose left slit or right slit. Behind the barrier, a screen with a detector that records single hits, one dot at a time. If photons are just particles choosing one slit each, then as you collect dots, you should see two smeared bands accumulate. But that is not what happens. At first, the dots seem random, but let the experiment run. As minutes turn into hours and the count grows, a pattern emerges, bright and dark fringes, just as if waves from both slits overlapped and interfered. The unavoidable conclusion is not that a tiny billiard ball split in half. The conclusion is that the quantum state describing the photon retains coherence between alternatives, through the left and through the right, so that their probability amplitudes add, with phases that can reinforce or cancel. Richard Feynman called this the central mystery. Send particles one by one, yet obtain a pattern that encodes their mutual interference as if each particle were interfering with itself. If you try to find out which slit the photon took, by placing a device to leave a path-specific mark, the interference disappears. Two smeared bands return. Remove the mark, and the fringes reappear. Knowledge, or more precisely, the possibility of distinguishing paths, matters. Act 4. Complementarity, how questions shape answers. Niels Bohr gave this behavior a name, complementarity. Certain properties, path knowledge and interference visibility, are mutually exclusive in a single experimental arrangement. You can build an apparatus to ask, through which slit did the particle go? Or you can build an apparatus to ask, how do the amplitudes from the two slits combine? You cannot, in a single run, ask both and receive both answers. It is not that the world coyly withholds information. It is that the conditions required to make one kind of information sharp blur the other. Interference needs indistinguishability, which path knowledge needs distinguishability. The line between them is not drawn by our emotions. It is drawn by the algebra of states and the physics of measurement devices that couple to the system. Act 5. Gentle marks and the role of indistinguishability. To see how gentle a mark can be and still matter, place linear polarizers over the slits. Orient one polarizer horizontally and the other vertically.
You have now labeled the paths with orthogonal polarization states. Even if no detector reads those labels, the light fields cannot interfere. The horizontal and vertical components are distinguishable. On the screen, the overall pattern loses fringes. But now, place a third polarizer at 45 degrees before the screen. This projects both orthogonal polarization components into the same basis. In a single stroke, you erase the distinguishing marks and restore indistinguishability. The fringes bloom again. No trickery is involved. You change the basis in which the system is viewed so that alternatives overlap and interfere. This is the spirit of the quantum eraser. Act 6. What's in a name? The quantum eraser demystified. The phrase quantum eraser sounds like a promise to scrub the past, but the device erases not events, but marks, correlations that would, in principle, someone to say which path was taken. In a classic eraser, you 1. Let a quantum system traverse two alternatives that can interfere. 2. Attach a distinguishing tag that kills interference in the summed pattern. 3. Later measure in a basis that mixes those tags, thereby erasing distinguishability within selected subsets. 4. Discover that when you sort the data conditioned on specific tag outcomes, interference reappears inside each subset, often as complementary fringes and anti-fringes that wash out when combined. The unconditioned pattern, the one you would see if you never used the eraser outcome to sort, shows no fringes once good witch path information is available. Only after you correlate detections with the right eraser outcomes does the wave-like order re-emerge in the appropriate slices. No time travel, no messages to yesterday, only the strict geometry of information. Act 7. Delayed choice, choosing the question late. John Archibald Wheeler added a twist. What if you wait until the last possible moment to decide whether your apparatus will reveal which path information or allow interference? In delayed choice experiments, a beam splitter can be inserted or removed on the fly. Or in entanglement-based erasers, the basis in which a partner particle is measured can be chosen at space-like separation or with a random number generator even after the signal photon has already hit the screen. The results are consistent and sober. You cannot change the past detection pattern at the screen by your later choice. What you can do is change how the joint dataset decomposes into patterns conditioned on your eraser measurement. When your final arrangement preserves distinguishability, the overall pattern is smooth, fringe-free. When your final arrangement projects away the distinguishability, interference appears, but only in the conditioned subsets.
Act 8. A concrete walkthrough, from source to eraser. Let's walk through one concrete optical quantum eraser, slowly and carefully. Source. A laser pumps a nonlinear crystal, creating pairs of entangled photons via spontaneous parametric down conversion. Each pair is born with correlated properties. Paths. One photon, the signal, heads toward a double-slit arrangement and then to a large, position-sensitive detector screen. The other photon, the idler, is routed through an optical maze with mirrors, polarizers, and beam splitters that can either preserve witch path labels or erase them. Tagging. The double-slit region encodes path information into polarization or spatial mode, so that, in principle, the idler's route can reveal which slit the signal took. Detection. The screen collects many signal hits. The idler meets detectors placed such that some measurement choices correspond to the witch path basis, others to the erasing basis, superpositions of paths. Sorting. If you look only at the screen, you see no interference. because which path information exists in principle carried in correlation with the idler. But if you post-select screen hits based on which idler detector fired, say those corresponding to the erasing basis, you uncover interference fringes in that subset. A complementary idler outcome yields anti-fringes. Add them back together and the ripples flatten, as they must. Timing. You can delay the idler measurements, even make the basis choice after the signal has long hit the screen. The correlations are indifferent to order in this sense. They respect causality. No signal travels backward in time. No controllable information passes faster than light. Act 9. Myths retired with kindness. It is tempting to hear these results as scandal. Let us replace scandal with understanding. We changed the past. No. You changed how you subdivided the data set in the present based on correlations set by the initial state and your measurement choices. Consciousness collapses the wave function. Consciousness is not a parameter in the Schrödinger equation. Measurement in quantum mechanics is about physical interactions that create robust records. Brains can host such records, so can photographic plates, Geiger counters, and cold silicon. The photon knows the future. The photon knows nothing. The quantum state encodes possibilities and their phases. The combination of initial preparation and final measurement defines what patterns can appear. We can send messages to the past. If you could, the world would tear. No quantum experiment, eraser or otherwise, has ever allowed controllable retrocausality. Interference in conditioned subsets cannot be used to signal. It appears only after joint data are compared.
Act 10. Why information matters. Coherence, tags, and traces. Interference requires coherence. Amplitudes from alternatives must remain phase-related so that cross-terms survive. A witch path tag, even if unobserved, can entangle the system with a marker, polarization, spin, and ancilla qubit. When you ignore, trace out the marker, the cross-terms vanish in the reduced description. That is a mathematical statement that every careful experiment has confirmed. Erasing, then, is not deleting history. It is projecting into a basis that recombines alternatives to reintroduce overlap. When the projection succeeds, interference reappears, but only within the conditional view provided by that projection. This is the grammar of information at work. What you can, in principle, know determines what interference you can, in practice, see. Act 11. Building without lying. Intuition that pays its debts. Analogies can help if we make them pay their debts. Consider music. Two notes played together can form a harmony richer than either alone. If you fix one string with a mute that breaks its phase relation to the other, the harmony dies. You hear two plain tones. Remove the mute or choose a listening mode that projects both into a shared resonance, and harmony returns. Nothing supernatural occurred. You changed the conditions for interference. Or photography. Two transparent patterns overlaid at the right angle produce a moe image, lines reinforcing and canceling. If you mark one pattern with a color your eye cannot mix with the other under white light, the moe disappears. Put on a lens that projects both colors into the same channel, and the moe returns. Again, you restored the conditions for overlap. Act 12. A history in rooms. Let's visit the rooms again, this time with a little more furniture. 1801. Young's lecture theater, a faint lamp, and courage. To see what no one expects to see is a strange kind of bravery. 1860s. Maxwell writes equations that look like poetry to the prepared eye. They do not sing about particles, they sing about fields. 1905. Einstein, who would later insist the moon exists whether we look or not, tells us light sometimes behaves as if it comes in lumps, a reluctant revolutionary. 1925 to 1927. Schrödinger's wave equation and Heisenberg's matrix mechanics, two languages for one world. Born insists that the wave is not a material ripple, but a calculator of probabilities. 1927, Bohr and Einstein argue in Solvay's rooms. Bohr, patient, says the question shapes the answer. Einstein, tenacious, asks for a picture that lets the moon be there anyway. 1960s to 1980s, lasers, down conversion crystals, single photon detectors, the lab learns to whisper with light. 1982 to 1999, Wheeler's delayed choice, Scully and Drule's conceptual eraser, and Zeilinger's implementations with entanglement. The metaphors step onto hardware. 2000s today, integrated photonics, superconducting nanowire detectors, high-efficiency down conversion. Quantum optics becomes an engineering discipline without losing its sense of wonder.
Act 13. The Lab Notebook. Components and Care. If you were to build a tabletop version, your notebook would list a single photon source, heralded photons from type 1 or type 2 SPDC in a BBO or PPK-TP crystal, pumped by a stabilized diode laser. Path definition, a precision double-slit or a Mach-Zehnder interferometer with matched arm lengths for phase stability. Tagging mechanisms, orthogonal polarizers at slits or path-dependent phase shifters or spatial mode converters. Eraser, a variable half-wave plate and polarizer set at 45 degrees, or a beam splitter and phase shifter to project idler paths into superposition bases. Detectors, a position-sensitive EMCCD or a scanning single-photon avalanche diode on translation stages, plus fiber-coupled SNSPDs for idler detections. Timing and coincidence, time-to-digital converters to correlate signal-idler pairs within a coincidence window. Stability, vibration isolation, thermal drift control, active feedback for path phase locking. The key is not exotic parts. It is discipline. Keep coherence. Control distinguishability. Document everything. Act 14. Delayed choice carefully unpacked. Wheeler's thought experiment imagines a Mach-Zehnder interferometer. A photon enters, a first beam splitter splits it into two arms, mirrors redirect, and a second beam splitter either recombines the arms, producing interference at the outputs, or is removed so the arms go to separate detectors, revealing which path. If you decide whether to insert the second beam splitter at the last moment, what happens? If the beam splitter is in place, the outputs show interference. Probabilities depend on the relative phase between arms. If it is absent, detections assign paths. The delay in your choice does not reach back to change a past. It completes the definition of the experiment. The particle is not a tiny person choosing whether to be a wave. The quantum state evolves continuously. Your late choice determines which observable, interference, or path is resolved at the end. In entanglement-based versions, the same logic manifests in correlations. Your basis choice for the idler determines which patterns you can reveal in the signal's detection record without any way to signal.
Act 15. What we mean by measurement. The word measurement carries baggage. In quantum mechanics, measurement is an interaction that amplifies a microscopic property into a macroscopic record, something robust against environmental noise. Such records can be stored on a screen, a photodiode's voltage pulse, a bit in memory. The line between microscopic and macroscopic is not metaphysical, it is practical. Decoherence, the rapid entanglement of a system with its environment, turns delicate superpositions into apparent mixtures by spreading phase information into degrees of freedom we do not track. The eraser uses this fact with finesse. It avoids uncontrolled decoherence by using controllable tags, then later recovers interference within those controlled degrees of freedom by choosing a basis that recombines them. If stray air currents, thermal drifts, or mechanical vibrations scramble the phase, no eraser can help. The poem has been smudged beyond repair. The art is in keeping the poem legible. Act 16. Gentle equations, spoken softly. We promised no math you couldn't hear, so listen. Two-path interference depends on a term like real part of YL, YR star, the real part of the product of the left path amplitude and the complex conjugate of the right path amplitude. Tagging the paths multiplies YL and YR by orthogonal marker states on ML and MR. When you compute what the screen alone sees, you trace over the marker. The cross term becomes real part of YL, YR star, bracket ML dot MR. If the markers are orthogonal, bracket MR dot ML equals 0. And interference vanishes. If you later project the markers into a new basis where superpositions overlap, bracket MR.ML becomes non-zero within that condition subset, and interference terms reappear there. That is the whole story, sung quietly. Act 17. Philosophy, but with seatbelts. Interpretations are where physics and temperament meet. You are allowed to prefer one as long as you keep your seatbelt fastened. Your preference must not contradict experiment. Copenhagen-style views emphasize the primacy of experimental arrangements and the role of measurement as a primitive. Many worlds says the wave function never collapses. Apparent collapse is just our experience of one branch among many. Bohmian mechanics adds hidden variables and a pilot wave that guides particles along definite paths, reproducing quantum predictions while keeping continuity of trajectories. Cubism treats the wave function as an agent's personal betting odds, updated by experience. Each of these speaks a different emotional language. Each can accommodate the double-slit and the quantum eraser. None offers a license to send messages to the past or to conjure outcomes by will. If you pick one, pick it for the questions it helps you ask, not for promises it cannot honor. Act 18. From paradox to practice. Why should we care beyond wonder? Because the same delicacy that makes interference possible also makes technologies powerful. Quantum key distribution relies on the fact that any eavesdropper who tries to gain which path-like information about your qubits disturbs their coherence, a disturbance you can detect. Quantum computing is an orchestra of amplitudes interfering to boost correct answers and cancel wrong ones across astronomical possibility spaces. Quantum sensors use phase sensitivity to measure time, fields, and motion with dizzying precision. The double-slit is not a parlor trick. It is the grammar school of quantum engineering.
Act 19. A letter to the patient mind. You may feel an ache, the ache of wanting the world to be simpler than it is. Let the ache be. The cure is not to pretend the world is simple. The cure is to speak clearly about the world we have discovered. The double-slit teaches us that coherence is precious, distinguishability is decisive, and information is physical. The quantum eraser teaches us that what seems lost can be found, if it was not destroyed, only hidden in correlations. Act
20. The quiet pause before we go deeper. Stand again with me at the wall. 2 slits, a screen, a source. Breathe. The next part of our journey will build a specific delayed choice quantum eraser step by step. Trace photons through mirrors and beam splitters, and watch how conditioned patterns compose and decompose. We will let the apparatus speak in its own voice, and then we will return to the human voice to talk about what it means to live in a world where the same question, asked for 300 years, still humbles us into wonder.
Act 21. Building the delayed choice quantum eraser, piece by piece. Let's place our components on the optical table and trace the journey of light with care. We begin with a pump laser, continuous wave, frequency doubled, stabilized in power and pointing. Its beam, a narrow ribbon of coherent blue or violet light, enters a nonlinear crystal. In that crystal, a small fraction of pump photons spontaneously convert into pairs of lower energy photons in a process called spontaneous parametric down conversion, or SPDC. These come in 2 broad flavors. Type 1, where both daughter photons share the same polarization, and Type 2, where they emerge with orthogonal polarizations. We choose Type 2 because orthogonal polarizations make excellent tags. Arrange the crystal such that the down-converted pairs emerge along 2 intersecting cones. Where the cones overlap, signal and idler photons are strongly correlated. We place irises to select narrow spatial modes from this overlap, and we fiber couple the outputs to control the paths with exquisite stability. One fiber leads the signal photon to a mask containing 2 slits. The other fiber carries the idler to a separate board, a labyrinth of polarization optics and beam splitters. At the slits, we mount polarizers. The left slit transmits horizontal polarization, the right slit vertical. That choice encodes path labels directly in polarization. Without further trickery, this labeling would destroy interference in the screen's summed pattern because horizontal and vertical states are orthogonal, perfectly distinguishable in principle. Downstream of the slits, the signal photon leaves the mask and travels to the detection plane, a cooled, low-noise camera capable of registering single photons. Each hit becomes a dot. We will let the dots accumulate. Meanwhile, the idler photon begins its own dance. On the idler board, we install 2 measurement pathways. One pathway, W for which path, separates horizontal from vertical polarizations using a polarizing beam splitter. Detectors at the PBS outputs deliver a crisp answer, H or V. If we correlate the signal's screen hits with these idler detections, we learn which slit the signal must have taken, and the corresponding subset of screen hits shows no interference. Pathway E, for eraser, projects polarization into the diagonal basis by a half-wave plate at 22.5 degrees, followed by a PBS. Now the detectors correspond to plus 45 degrees and minus 45 degrees superpositions of H and V. These outcomes erase the path label within that conditioned subset. When we correlate the screen hits with each eraser detector, we recover beautiful interference and anti-interference fringes. Summed together, the 2 eraser-conditioned subsets wash out to the smooth envelope, as they must. A fast electro-optic switch selects between pathway W and pathway E on the fly, driven by a random bit stream from a quantum random number generator. We place extra fiber delay in the idler arm so that its measurement choice can be made after the signal photon has already struck the screen. We timestamp every detection event with picosecond resolution and record coincidences in a narrow window. The table hums softly with cooling fans and the faint click of detectors. This is the delayed choice quantum eraser in a nutshell. But a nutshell isn't enough. Let's live inside it.
Act 22. The signal screen. What you see, what you don't. If you were to sit by the screen and watch dots appear without any access to idler information, here is what you would see. A broad, smooth distribution shaped by diffraction through the two slits, but no fringes. The label H on one path and V on the other has killed interference in the marginal distribution. The cross term that would produce ripples is gone because H and V are orthogonal. They carry which path information in principle. Hours later, after millions of dots, the screen still refuses to reveal the ghost of interference. It's tempting to interpret that as a loss. It isn't. The structure is not destroyed. It is sequestered inside correlations with the idler's polarization. The poem has not been burned. It has been written in a cipher that requires a key. Later, when we bring the idler data to the table, we can unlock the cipher. We split the signal screen hits into 4 piles, depending on which idler detector fired: H, V, plus 45, minus 45. The H and V piles, our which path subsets, show no fringes, just the envelope you expect from particles choosing single slits. The plus 45 pile shows a clean interference pattern with bright maxima where the HV summed pattern was flat. The minus 45 pile shows the complementary anti-fringes, where plus 45 has a peak, minus 45 has a dip. Add plus 45 and minus 45 together, and you return to the smooth envelope. No violation of causality, no trick. Just conditioning versus marginalizing, correlation versus ignorance. Act 23. A map of correlation. Why slicing matters. Correlation is not an afterthought. It is the fabric on which quantum patterns are embroidered. When we say erase, we mean measure in a basis where the which path marks do not distinguish alternatives, and then slice the data according to those measurement outcomes. The mathematics of tracing and conditioning says exactly this. Marginal view, ignore the idler. You trace over its degrees of freedom. Orthogonal tags make cross terms vanish. No interference. Conditional view. Select screen hits linked to a particular idler outcome in a superposition basis. Cross terms reappear within that slice. Interference blooms, but only inside the conditioned subset. The philosopher in us wants the marginal view to tell the whole story. The experimenter in us knows that the whole story lives in the joint distribution. Quantum mechanics is not coy. It is consistent. It tells you that different questions carve the same dataset into different, honest patterns. Act 24. Variations, spatial mode tags, and Mach-Zehnder erasers. Polarization is not the only way to tag paths. We can use spatial modes, slightly tilt a glass plate behind one slit to introduce a small angle, tagging one path with a tiny deflection. Or we can push the whole setup into a Mach-Zehnder interferometer, which is the grown-up cousin of the double-slit. In the Mach-Zehnder, a first beam splitter divides the path into 2 arms. Mirrors redirect the arms to a second beam splitter that recombines them. If the arms are balanced, constructive interference sends photons to one output port and destructive interference empties the other. Insert a device, say a phase shifter, in one arm, and the detector counts oscillate as you tune the phase. To tag which arm a photon takes, you can couple an ancillary degree of freedom, spin, frequency, time bin, or entangle the photon with a partner. The eraser then consists of choosing a measurement basis for that ancillary system that either reveals which arm or projects into superpositions that erase the tag. The patterns you reconstruct, again by conditioning on outcomes, mirror the double-slit story. Fringes in one slice, anti-fringes in the complementary slice, and a smooth sum overall.
Act 25. Time bin encodings and the taste of delay. One elegant variation uses time bins. Split a pulse into early and late components with an unbalanced interferometer. Now your two paths are two arrival times, distinguishable if your detectors can resolve them, indistinguishable if you erase the timing information. Entangle the signal and idler in time bin superpositions. On the idler side, choose to measure in the time basis, which reveals which bin, or in the superposition basis, which erases timing labels. On the signal side, reconstruct interference in the conditioned subsets by scanning a phase shifter in its own interferometer. Time bin encodings make the delayed choice aspect visceral. You can store the idler in a long fiber spool and measure it milliseconds after the signal was detected. The logic holds. The past at the signal screen is not rewritten. The present carving of data reveals patterns latent in the whole. Act 26. Entanglement swapping and erasing by association. Another layer. Entanglement swapping. Suppose we produce two entangled pairs, A and B and C and D. We never let A and D meet. Instead, we perform a joint measurement on B and C that, depending on the outcome, projects A and D into an entangled state after they have already been detected in some runs. The correlations between A and D that appear in the post-selected dataset feel like a conjuring trick, but they are expressions of joint structure imposed by the swapping measurement. Now, build a double-slit-like structure into A's and D's paths, perhaps by encoding which path-like labels into their polarization. Use the BC joint measurement to choose whether to preserve or erase those labels in the effective state of A and D. When you later sort A's and D's detection records by the BC outcome, interference can reappear inside the appropriate slices. The language of after-the-fact erasing returns, but the architecture of explanation remains. No backward causation, only conditioning on correlations established by the total experimental context. Act 27. The role of randomness, free choices, and clean stories. We leaned on a random number generator to choose measurement bases. Does that matter? It matters if you care about closing loopholes. If the apparatus were to choose bases in a way that correlates with some hidden variable, a mischievous classical model might mimic some Cuban features. Using a high-quality random source, better still, choices made at space-like separation, ensures that the basis selection is uncorrelated with the particle's hidden instructions, if any exist. Zeilinger's group and others have pushed this to extremes, even using starlight to set measurement bases. The result holds. Interference appears only where and when the algebra of the joint state says it can, never as a controllable signal.
Act 28. Decoherence, the quiet enemy of poetry. All our talk of erasing assumes we can control the tags, but the world is noisy. Air currents jiggle path lengths. Thermal drift shifts phases. Vibrations and magnetic fields nudge components. The system leaks information to the environment. Tiny, uncontrolled witch path marks that we cannot erase because we do not know how they are written. This is decoherence. It takes superpositions and spreads their phase relationships into a vast bath of degrees of freedom. From the perspective of the small system, interference is gone, irrecoverably in practice, even if not in principle. Decoherence explains why macroscopic objects behave classically. It is why cats are either awake or asleep, why baseballs have trajectories, and why your coffee mug is not in a shimmering superposition of being on the desk and on the floor. The quantum eraser's magic works only in the garden before the vines of the world grow over the gate. That is not a failure. It is a boundary set by scale and noise. Act 30. Feynman's voice, heard softly. Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He didn't mean we can't use it. We use it with terrifying success.
He meant that our pictures, our human metaphors, cannot hold all the rules without spilling mystique on the floor. The double slit for him was the crucible where our metaphors crack. He urged us to calculate, to let the amplitude machinery do its work, then to be humble about the stories we tell afterward. The quantum eraser doesn't change that advice, it refines it. Calculate the joint state. Decide what you are tracing out and what you are conditioning on. Only then reach for words. Act 31. The human feeling. Awe without alarm. It is tempting to turn awe into alarm, into late-night whispers that the universe is responsive to our whims, or that time folds under our stare. Resist that temptation. The true awe here is cleaner. It is awe at a world where information is physical, where indistinguishability is not ignorance, but a resource, and where correlations carry structure that single views cannot see. It is awe at the discipline of an experiment that can keep coherence alive long enough to paint with it. It is awe at the patience of light.
Act 32. Questions you might ask in the dark. If interference returns only in conditioned subsets, does that mean the interference was really there all along? Answer: it was there as potential in the joint state. Reality in quantum mechanics is not only about what is measured, but about what could be measured and how those possibilities are structured. The fringes are not ghosts, they are conditional facts. If I choose the eraser basis after the signal hits the screen, do I decide whether the signal had a wave or particle nature in the past? Answer: you decide how to read the joint record. The past detection does not change. The meaning of that detection relative to the idler's record acquires new structure. Why can't we use this to send messages? Answer: because the marginal distribution at the screen never changes with your basis choice. Only the joint post-selected distributions differ, and you need to compare data sets, requiring classical communication to see the difference. Is there an interpretation where the particle really took one path and hidden variables explain the rest? Answer: Bohmian mechanics offers definite paths guided by a non-local pilot wave. It reproduces all standard predictions, including erasers and delayed choice, by allowing the guiding wave to carry phase information that shapes outcomes non-locally. But it does not enable signaling or time travel, and it pays a price in non-locality. Act 33. A slow walk through a real data set. Imagine we've run our apparatus for a day. We have 1,000,000 coincident pairs. We plot the raw signal screen hits, a smooth envelope, no fringes. Then we sort the hits by idler outcome. H subset, 250,000 events. The histogram across the screen shows the broad two-hump distribution characteristic of single-slit contributions added without interference. V subset, 250,000 events. The same envelope. Put H and V together and you recover the raw. Plus 45 subset, 250,000 events. The histogram reveals strong fringes, peaks and valleys at positions predicted by the known slit separation in wavelength, modulated by the diffraction envelope. Minus 45 subset, 250,000 events, the complementary anti-fringe pattern, peaks where plus 45 has valleys. We compute visibility, V equals I max minus I min over I max plus I min within the conditioned subsets. We find V near the theoretical limit set by our coherence and alignment. We compute which path distinguishability, D, from the HV data. We verify Englert's inequality, V squared plus D squared less than or equal to 1. The numbers sing in tune.
Act 34. Englert's inequality, a compact law of complementarity. Englert formalized complementarity in a crisp inequality. If D is the path distinguishability, the degree to which a measurement can reveal which path was taken, and V is the fringe visibility, the contrast of the interference pattern, then V squared plus D squared less than or equal to 1. Equalities hold for idealized setups. Intuitively, the more reliably you can tell the path, the less contrast your fringes can have, and vice versa. The quantum eraser dances on this curve. The H over V slices maximize D and minimize V. The plus-minus 45 slices minimize D within the conditioned view and maximize V. This inequality is not just a bound, it is a compass. It tells you where you are in the space of possibilities even before you assemble the apparatus. Act 35. The cost of post-selection. One might object, post-selection feels like cheating. You're throwing away data to recover a story you already wanted. But post-selection is not a lie, it is a lens. If your question is, what pattern emerges when which path marks are erased, then conditioning on the eraser outcome is the right way to ask. If your question is, what do we see if we ignore correlations, then the raw, unconditioned pattern is the right answer. Neither is privileged, both are honest answers to different questions. In practice, the cost of post-selection is efficiency. You learn something sharp about a subset at the price of discarding other events for that question. Technologies that exploit interference, like quantum computing, are built to avoid that cost by maintaining coherence throughout the whole computation rather than recovering it after the fact. Act 36. Beyond photons, atoms, electrons, molecules. Photons are cooperative. They don't bump into each other easily, and optics gives us beautiful tools. But the double-slit logic stretches beyond light. Experiments with electrons, neutrons, and even massive molecules, Buckminster fullerene, C60, and larger organic complexes have shown interference patterns when conditions preserve coherence. Which path tagging and erasure can be implemented via spin states, internal energy levels, or magnetic phase shifts. Decoherence becomes fiercer as mass grows. The environment writes its graffiti faster. Still, when we keep the canvas clean, even a molecule the size of a small protein can paint fringes in the right vacuum and at the right temperatures. The grammar is universal.
Act 37. The subtlety of which path. We keep saying which path, but quantum mechanics warns us, paths are not little roads the particle could have taken in the classical sense. Path labels are basis states in a Hilbert space. Sometimes they correspond nicely to spatial routes. Sometimes they are abstract modes, early versus late, polarization H versus V, arm A versus arm B. What matters is distinguishability, not geography. If two alternatives couple to distinct records, interference dies. If you erase the distinction in a controlled way, interference can revive in the right view. The map is in the math. Act 38. A thought experiment. The honest alien. Imagine an alien who cannot see polarization. Its detectors are blind to that degree of freedom. To the alien, the H over V labeling we used is invisible. If it runs the double slit, labels paths by H over V, and looks only at the screen, it sees no interference and might conclude this apparatus does not preserve coherence. But if the alien learns to build an eraser, a device that projects H and V onto diagonal superpositions, and then slices the data accordingly, it will see interference. The alien has not learned a new fact about light, it has learned a new basis in which to ask the question. We are all that alien at first.
Act 39. Causality, locality, and no signaling. Let's collect the big three principles that people worry about. Causality. Effects do not precede causes. The eraser respects this. The screen's marginal pattern never depends on later choices. Locality. No influence travels faster than light. Entanglement correlations are non-local in the sense that joint statistics cannot be explained by local hidden variables, but they cannot be used to send messages. The eraser plays by that rule. You need classical communication to compare subsets. No signaling. The statistics accessible to any local observer are independent of distant measurement choices. The eraser exemplifies this. You cannot know from the screen alone whether the idler basis was which path or erasing. Only after datasets are brought together do patterns differ.
Act 40. Language audit. Words that help, words that hurt. We owe ourselves a language that doesn't betray us. Helpful. Interference requires indistinguishability. Which path information can exist in principle? Erasing is projecting into a basis that recombines alternatives. Hurtful. The particle decides to be a wave. Observation creates reality without careful qualifiers. We changed the past. It's not that poetry is banned, it is that poetry must report to duty when the math calls. Act 41. How to teach this to a bright 12-year-old. You don't need to hide the truth, you need to scale it. Show them water waves at 2 slits. Show light at 2 slits. Show the 1 photon at a time buildup. Explain that in math we add not probabilities, but complex waves whose squares give probabilities. Explain that labels kill overlap. You can't add apples and oranges unless you slice them both into juice. Show that erasing is making juice. You can make the 12-year-old laugh at that. They'll remember. Act 42. The emotional arc of a lab day. Morning, alignment. The first photons coaxed into fibers. The slow thrill of first coincidences. Midday, frustration. A fringe visibility that won't climb past 60%. The discovery of a misangled half-wave plate. Afternoon, the quiet gasp when the +45 histogram prints with perfect peaks and the -45 histogram prints with perfect dips. Evening, data logging, coffee cooling, the dignity of error bars. Night, the last walk past the screen, still popping with single photons like stars. If you have never done it, take a moment to feel that you could. Act 43. Common pitfalls and honest fixes. Path length mismatch. Interference visibility collapses if the relative phase jitters during acquisition. Fix, active stabilization or shorter acquisition windows. Imperfect orthogonality. If H and V are not perfectly orthogonal due to misalignment, residual fringes can leak into the unconditioned pattern. Fix, realign, and quantify extinction ratios. Detector saturation. Bright background washes out single photon sensitivity. Fix, better filtering and timing discrimination. Coincidence window too wide. Accidental coincidences dilute conditioned patterns. Fix, tighten timing windows or use better TDCs. Post-selection bias. Cherry-picking outcomes can fool oneself. Fix, pre-register analysis protocols and report all slices.
Act 44. A pause for philosophy. Meaning without metaphysics. We are allowed to ask, what is the world like if these are its rules? Perhaps the safest answer is modest. The world is such that our most powerful descriptions are about possibilities constrained by amplitudes, not certainties traveling down pre-drawn lanes. Facts appear when interactions write records. Between records, structure lives as phase relationships that can be used or lost. The eraser doesn't crown observers, it crowns arrangements. It suggests that reality is relational, not because minds make it so, but because
interactions do. Act 45, From Lab to Life, a human-scale analogy carefully drawn. Imagine you plan 2 possible days, one at a museum, one on a mountain. If you keep your morning open, no commitments, the day is like a superposition. Possibilities coexist. If you book a non-refundable tour at the museum, you've tagged your path. The mountain day's interference with the museum day is gone. You'll never accidentally end up among pines. If later a friend calls and offers to cover the tour cost regardless of what you do, some of the distinction is erased. The choice reopens. Still, you cannot add hours. You cannot be in both places at once. The analogy fails if pushed too far, but it carries the whisper. Tags constrain futures. Their erasure can restore options only within what was not already spent. Act 46, The Boundary of the Miracle. We should say this clearly. The quantum eraser is not an engine of miracles. It is a microscope for structure. It lets you see that what looks like a loss can be a hiding. It lets you rescue interference not by bravado, but by respect. Respect for basis, for correlation, for conservation of information. The miracle, if we insist on the word, is that the universe lets us do this at all. Act 47. Preparing for the final movement. We have circled the apparatus, tuned its voice, and listened to its song. In the final movement of this episode, we will widen the lens again, compare interpretations more explicitly against the eraser, walk through a cinematic narrative tying 3 centuries into one thread, and leave you with a map. How to think when your next wonder arrives at your door wearing the same paradoxical smile.
Act 48. 3 interpretations, 1 experiment. A clear contrast. Let's lay 3 interpretations side by side and let the quantum eraser question each, politely but firmly. Copenhagen-flavored minimalism. The wave function is a tool for assigning probabilities to measurement outcomes. It evolves unitarily until a measurement yields a record, then we update the state to reflect that record. In this view, the eraser is a model case. Distinguishability introduced by tags removes interference in the marginal. A later measurement, in a basis that recombines the tags, allows interference to be seen in the conditioned subsets. There is no talk of world branches, there is no story about particles secretly knowing paths. There is only the rulebook. Prepare, evolve, measure, update. Many worlds, Everett. The universal wave function always evolves smoothly, never collapsing. In the HV-tagged double-slit, the signal plus idler plus apparatus becomes entangled into branches corresponding to H and V. When we measure the idler in the diagonal basis, we further branch into plus and minus sub-branches. In the plus branch, the signal interference pattern shows peaks. In the minus branch, it shows troughs. The reason the unconditioned signal shows no fringes is that when you add the plus and minus branches without knowing which you inhabit, peaks and troughs cancel. No contradictions, no retrocausality. But the price you pay is a vast ontology, many branches, all real. Bohmian mechanics, pilot wave theory. Particles always have definite positions. A guiding wave, the pilot wave, evolves according to Schrödinger's equation and directs particles along trajectories. In the double slit, the guiding wave passes through both slits, creating an interference pattern in the pilot wave structure, but the particle goes through one slit. If you introduce HV tags that couple to an ancilla, the pilot wave structure changes, destroying the interference in the effective guidance felt by the particle in the marginal signal description. When you measure the ancilla in the diagonal basis and post-select, you effectively select sub-ensembles guided by pilot waves with different phases, yielding fringes and anti-fringes.
Again, no signaling or retrocausality. Non-local effects live in the pilot wave's holistic guidance. Each interpretation translates the same algebra into a different story. The experiment demands consistency with v squared plus d squared less than 1, with no signaling, with the appearance of fringes only in conditioned subsets when tags are erased. All three deliver. Your choice among them should be guided by what explanatory costs you're willing to pay: conceptual overhead, ontology, and taste, not by promises to overturn facts. Act 49. A cinematic walk through 3 centuries. Let's take a breath and step into a cinematic sequence, a slow montage that threads 300 years with one unbroken line. Fade in a candlelit room in 1801. Thomas Young, hands steady, aligns a slit plate. The image softens into a ripple tank, water waves spilling through paired apertures, stripes of light and shadow drifting across a white tile. Cut to a chalkboard, 1865. Maxwell's hand arcs equations that bind electricity and magnetism into one song. The camera pans to a gleam of metal under ultraviolet light. Electrons leap. Einstein's face is intent. The film's grain deepens. Planck, Bohr, Born, Heisenberg, Schrödinger, each frame a different texture of doubt and daring. We follow Feynman's finger as it traces 2 slits on a lecture hall blackboard. The frame changes to a dark lab in the 1980s, a green laser, a BBO crystal, subtle clicks on speakers as single photons announce themselves. A PBS rotates, a half-wave plate turns, a histogram on a beige monitor erupts in a fringe pattern. It flips to the complementary anti-fringe. A hand writes "no time travel," underlined twice. The pace quickens, integrated photonic chips glint, superconducting nanowire detectors bloom at liquid helium's breath. A server fan hums as petabytes accumulate. The montage ends where we began: a quiet wall, 2 slits, and the patience of light. Act 50. A deep dive into visibility, distinguishability, and coherence. We've invoked visibility V and distinguishability D. Let's nurture them into intuition you can feel. Visibility is the contrast. How much brighter are the bright bands than the dark ones? It is fragile because it relies on phase alignment across the apparatus. Any jitter smears it. Distinguishability is the confidence with which you can tell paths apart. Either in practice, you actually measure a tag, or in principle, a tag exists that could be measured. It is robust in a different way. Once marks are written into orthogonal degrees of freedom, path alternatives are truly different. No amount of wishful thinking lets them interfere in the marginal view. Coherence is the resource that lets amplitudes add. Think of it as timing, phase, and sameness across alternatives. Where coherence goes, interference follows. Englert's inequality, v squared plus d squared less than or equal to 1, is the geometry that stitches these intuitions together. It is a circle's quadrant in abstract space. Move toward more v and you must accept less d. Move toward more d and v must recede. The eraser lets you step from one corner to the other, not by breaking the geometry, but by changing how you slice the world. Act 51. The subtleties of in principle. In principle is a phrase that asks for honesty. If a record exists somewhere that could, even in principle, be accessed to reveal which path, interference in the marginal is gone. You don't need to read the record, the universe has already written it. The photon's polarization, a scattered air molecule's momentum, a phonon in a slab, these are records. If they are orthogonal for different alternatives, the cross terms vanish when you ignore them. The eraser works when those records are confined to degrees of freedom you can access and manipulate coherently. If the record has bled into 100 million air molecules, you cannot recollect it. The poem is now not merely hidden, it is shredded. This is the line between control and the world's indifferent entropy. Act 52. A human interlude. A letter to curiosity. Curiosity, you have been patient. You have followed photons through slits, screens, splitters, and stories. You have forgiven language for its clumsiness and asked math to hum softly in the background. You have watched interference be born, die, and be reborn within the boundaries of honesty. You have allowed the experiment to reshape you, gently, without humiliation. In return, the experiment has given you a grammar you can use on other days. When life offers two paths, you may notice what makes them distinguishable and what might be erased. You may sense where interference could live and where it cannot. This is not mysticism. It is a habit of clarity.
Act 53. Beyond optics. Solid-state and superconducting implementations. Photons are not the only carriers of coherence. In solid-state circuits, superconducting qubits patterned on chips, engineers build interferometers in energy space. A qubit in a superposition of 0 and 1 acquires a relative phase under different drives. Interference in readout reveals that phase. Which path tags become extra qubits or resonators that become entangled with the main qubit, destroying visibility in the marginal. Erasers project those ancillas into superposition bases before readout to recover conditional fringes in tomography. The same v² plus d² bound lives here, translated into Rabi angles and dispersive shifts. In quantum dots and NV centers, path-like alternatives live in spin sublevels and orbital pathways. Microwaves and lasers do the job of half-wave plates and PBS cubes. The grammar persists. Act 54. Quantum foundations as craft. Foundations can look like philosophy, but on the bench they feel like craft. The craft is to make a promise to the world. I will keep coherence alive. I will control tags. I will measure cleanly. And then to keep it. The data you get is the world's reply. If you are careless, the reply is muddy, and you might mistake mud for mystery. If you are careful, the reply is a clear yes or no to a precisely posed question. The quantum eraser's beauty is that it asks precisely and listens carefully. Act 55. Common misreadings and their remedies. Misreading. If we choose the eraser basis late, the earlier photons knew we'd choose it. Remedy. Replace knew with we're part of a joint state that allowed correlations consistent with either choice. Late choices affect which correlations you can reveal, not past facts. Misreading. Erasers prove that observation creates reality. Remedy. Clarify observation as physical measurement producing a record. Reality includes records written without humans present. Misreading. Interference in post-selected data is a data mining artifact. Remedy. Pre-register analysis. Calculate expected patterns for each post-selection outcome and verify that complementary slices sum to the raw distribution. Act 56. A walkthrough you can hear with eyes closed. Close your eyes and listen. A laser breathes. A crystal hums with the possibility of pairs. A tiny mirror angles a path. A slit plate waits like a doorway to a quiet chapel. Photons arrive one at a time, each a soft knock you cannot hear, but which leaves a mark on a digital retina. The screen dots collect like rain beginning. Somewhere else on the table, a fast switch ticks between "tell me the path" and "tell me the pattern." If we could listen to the idler detectors, we would hear two voices, one that names paths, one that names superpositions. Later in software, we let those voices sort the rain. In one pile, the rain says only, "I came through one roof or the other." In another, it says, "I came from both, and I am music." The room says nothing. The room has learned to say nothing very well.
Act 57. The ethics of explanation. Explaining quantum erasers invites a responsibility. Do not trade precision for applause. The public deserves the truth trimmed to their attention, not to the speaker's convenience.
If you feel the tug to say, "We changed the past," to light a spark, resist. There are sparks enough in the truth. Tell them that information is physical, that interference is a grammar, that distinguishability is a knife that cuts, and that erasers are a needle that mends. If they want more, they will come back. They always do. Act 58, a practical appendix for builders. If you are tempted to build, here is a short spoken bill of materials and practices that pay off. Light source, a 405 nanometer diode laser, power stabilized. Keep it below the crystal's damage threshold. Warm-up drift matters. Nonlinear crystal, PPKTP or BBO for SPDC. Calibrate phase matching temperature for stable pair production. Filtering, narrowband interference filters to enforce spectral indistinguishability, spatial filters for mode cleaning. Mechanics, kinematic mounts, low drift posts, and a floated optical table. Use irises to tame wander. Label everything. Polarization optics, quality half and quarter wave plates, high extinction PBS cubes. Calibrate angles with a polarimeter. Detection, EMCCD or SCMOS with single photon sensitivity for the screen, or SNSPDs or low dark count SIAPDs for idlers. Synchronize with a fast TDC. Software, coincidence counting, histogramming, and post-selection pipelines. Simulate expected patterns and overlay them with live data. Hygiene, dust covers, temperature control, and patient hands. The universe rewards care. Act 59. When interference fails, reading the tea leaves. Sometimes the fringes won't come. Don't panic. Read the tea leaves. If the unconditioned pattern shows weak residual fringes, your tags aren't orthogonal. Increase extinction ratios. If the conditioned fringes are shallow across both plus and minus, suspect path instability. Phase drift smears peaks. Stabilize or shorten acquisition times. If the witch path subsets show fringes, your witch path measurement is not projective. Fix the PBS alignment or detector crosstalk. If nothing looks right, simplify. Remove pieces until a basic two-slit interference returns, then reintroduce tags and erasers one by one.
Act 60. A Minute with Wheeler. Wheeler loved big questions wrapped in small experiments. His delayed choice provoked us to notice that the definition of an event in quantum mechanics is woven from the entire experimental context, the arrangement at the end, not just the start. He mused about participatory universes and information as the bedrock. Whether you follow him that far or not, his craftsmanship lives in the eraser. Choose the meaning of data not by decree, but by apparatus. Act 61. Poetry with its feet on the ground. Let a few lines of poetry stand, but keep their boots muddy. Two doors, one hallway of light. A whisper passes both and returns as song, unless we hang a nameplate on each door. Later, if we take the plates down together, the echo remembers how to harmonize. The bricks do not change, the room does. Act 62. The Classroom Module. How to teach in 90 minutes. First 15 minutes, history and stakes. Young to Feynman, the problem and why it is the only mystery. Next 20 minutes, live or animated two-slit build-up, one photon at a time. Show interference emerge. Next 20 minutes, introduce path tags, HV. Show interference vanish in the marginal. Next 20 minutes, eraser with plus or minus 45. Show conditioned fringes and anti-fringes. Emphasize no signaling and Englert's inequality. Final 15 minutes, Q&A. Field the usual suspects, time travel, mind over matter, interpretations. Provide a handout that states, interference requires indistinguishability. Which path information kills interference? Erasing distinguishability in a correlated basis restores interference in conditioned subsets. v squared plus d squared less than or equal to 1. Act 63. A gentle rebuttal to pseudoscience. When someone says, erasers prove thought shapes reality, answer kindly. Thought can shape apparatus. Apparatus shapes questions. Questions shape which facts can appear. That is beautiful enough. We do not need to claim more. If they insist, invite them to the lab. Invite them to align a wave plate and watch a histogram turn from smooth to rippled and back. Let reality be the conversation stopper.
Act 64. The edge of the map. Open questions. The double-slit and the eraser do not exhaust quantum foundations. They touch deep questions. Objective collapse models. Could there be a physical mechanism that collapses superpositions above a mass or complexity threshold? Experiments push limits, but no decisive evidence yet. Quantum gravity. How does space-time and superposition coexist? Can gravity carry which path information and cause decoherence? Tabletop experiments with massive superpositions are nibbling at this. Psi-ontology versus psi-epistemology. Is the wave function a real physical field or a state of knowledge? The Pusey-Barrett-Rudolph theorem nudges us toward realism under certain assumptions, but the debate remains alive. These are rooms off the main hall we have walked. The same grammar will guide us when we enter them. Act 65. A final case study. Polarization and tangled eraser with imaging. For a last concrete study, picture this. We generate polarization-entangled photon pairs in the Bell state. Bracket HH plus bracket VV over square root of 2. The signal passes through a double slit that imparts slight, known phase shifts between H and V for each path, effectively encoding which path marks in joint polarization path space. The idler travels to a measurement stage that can choose between H and V, which path, and plus and minus, eraser, bases. We place a high-resolution imaging system at the signal plane, mapping transverse momentum to position. When we condition on idler outcomes in the plus-minus bases, we see sinuous interference curves whose phase depends on the idler detector, a spatial hologram of correlation. When we condition on H or V, the curves flatten. We sweep a tunable phase plate behind one slit and watch the fringes glide across the screen in lockstep with a phase, proof of coherent control. We verified that summing complementary slices always returns the same marginal distribution. The apparatus becomes a chalkboard on which algebra writes pictures. Act 66. The sound of enough. There is a moment when explanation must concede the field to experience. You have the rules, you have the apparatus, you have the map of pitfalls and the grammar of information. There is nothing left to add that would not be repetition or ornament. The sound you should hear now is the small, confident click of understanding settling into place.